Hi and a very good day. So in this video session, we will look at the properties of non-stationary time series. Okay, so in general, if the series does not fulfill the stationary condition as we discussed before, we say that we define the series as non-stationary series. Okay, so basically we can categorize it into two classes, where a series that is not constant around the mean or level, and also not only it's being time dependent, it also show an increase in the variability. Okay, so I have these two figure here to represent some example of non-stationary series. Okay, uh, okay, based on this graph in my left. Okay, there is actually changes on level here, over time. Okay, and based on my right figure here, the magnitude of the fluctuation is different. Okay, there is actually structural changes over time. So we say that when we see this kind of pattern, we might say that this time series might be not stationary. Okay, and just for introduction, okay, non-stationary can be made stationary, okay, by using the process what we call it as differencing method. Okay, so this differencing method I will discuss later on in the next topic. Okay, right, so let's take a look at one of the example of non-stationary time series. Okay, we call it as a random walk process. Okay, why we call it as a random walk process? Okay, suppose that now we have a sequence of our error terms, where our error terms now is a random variables with zero mean and variance equals to sigma square. Right, and we construct our observation by, okay, suppose that at y1, okay, here is equals to equals to epsilon 1, okay, and then y2 here is equals to epsilon 1 plus epsilon 2 up until yt, where epsilon 1 plus epsilon 2 plus, okay, we keep adding our error term in the our observed time series. Okay, so this is where the terms random walk comes. Okay, we say that this is the step that these particular error terms are actually interpreted as the size of the step taken, whether it be forward or backward, okay, along the number line. While for this particular series, this is actually the position of the random walker at time t. Okay, so that's why we call it as a random walk. Okay, so alternatively, we write this particular process as yt equals to yt minus 1 plus the error terms, where the error term is the error term here, okay, it have, okay, zero mean and sigma square of variance. Okay, so let's take a look at why we say this random walk is not stationary. Okay, by looking at the mean function and the variance function. Okay, for the mean function, based on this particular based on this, okay, we define the mean and variance for random walk. Okay, the mean function and the variance function for our random walk process. Okay, so let's take a look at the mean. Okay, since that we say ET have zero, zero mean and variant of sigma square. Taking the expected value of our YT, will produce mean function of equals to 0 for all t. That's for that is the variance for random walk process. Okay, let's take a look at the mean function for the mean function for random walk. Let's take a look at the variance function for random walk. Okay, again we use the same presentation. Okay, but based on this, we know that for each of these error term variant, we will keep adding the the variant for each step. So what happened now, our variant of YT, if our YT have a random walk, if our YT is a random walk process, it will produce the variance of T times the variance, where this T is for how many observation, how many steps that we measure our YT. Okay, based on this definition, based on this variant function, we say that the process variant increase linearly with time. More time added, it means that your variant will keep increasing. Note that even though the theoretical mean function is 0 for all time point, even though that is still 0, the fact that the variant increases over time and the correlation between process value nearby in time is nearly 1, we should expect long excursion of the process away from the mean level of 0. It means that because of this particular variance that increase linearly with time, it will affect the mean level of our YT here. So that's the thing. So this is what we call it as random walk, and we have another type of non-stationary time series here. We call it as random walk with drift. Drift here is this particular element is added in our random walk, where we have the drift element. Says that it fluctuates around a constant mean of mu. So again, when we here we emphasize the theoretical properties of each series. So for this particular random walk with drift, it can be shown that by using a process of substitution, if we want to forecast the one step ahead value, the value is actually the value of our forecast is simply as YT plus K times the drift the drift element, the constant drift element, right? So that is this definition. By taking the realization again, when we're talking about the realization, theoretically this is how we define our random walk with drift. And I have these figures to differentiate between random walk with drift and random walk without drift. This black line is actually random walk with drift, while this blue line is random walk without drift. I think that's all for this video session. Thank you for listening. Bye.